Yesterday, we looked at what happens to excess charges on or in conductors. Now, a conductor can get excess charges, excess electrons from any one of a number of sources. Maybe it's a lightning strike, or maybe it's charging by friction, rubbing something against it to get excess charges. Whatever the cause, my conductor has extra electrons, excess charges. What's going to happen to those electrons? Well, they're going to repel each other. You've got, in this case, 3 extra electrons. Maybe you got 1,000 protons, well, you got 1,003 electrons. Maybe you got 10 million protons, then you got 10 million and 3 electrons. It's not that we have 3 electrons, we have 3 excess electrons. And that's what we're talking about here, is these excess electrons. They're going to repel each other, and they're going to repel each other as far away as they possibly can. They're going to get as far away from each other as they can. Now, what happens when they get as far away as they possibly can? Well, they stop moving, and they stop moving because the forces end up balancing out. They're in a state of equilibrium. We call it static equilibrium. Not moving, at rest, okay, force is balanced. Now, what's the pattern going to look like? What's the distribution going to look like when they reach this point of static equilibrium? Yesterday, we did the analysis of all 3 of these charges. Today, I only want to do one because it's a review. Let's pick charge number 2. Charge 2 is repelled by charge 1. It's pushed away by charge 1. We're going to call that the force of 1 on 2. 2 is pushed away by 3. It's repelled by 3 in this direction. We'll call that F32. Now, those 2 forces combine to give me a net force acting on charge 2, which is this way. It's outwards, toward the surface. You would find, if you did the same analysis, that the force on this one was outwards, and the force on this one was outwards as well. The net force on all of these excess electrons is outward toward the surface. And that's where the electrons go. The excess electrons, that is, they go to the surface. Now, why don't they go beyond the surface? I say they go out to the surface. There's still a force pushing them outwards, right? Why don't they keep going? Yep. Yeah, usually they don't go anywhere because the air surrounding it is an insulator. If it happened to be this conducting sphere being bathed in mercury, let's say, which is a conductor, well, then the electrons would keep going. But generally, we're talking about the sphere going to be in air, which is a pretty good insulator. So most times the electrons will stop when they get to the surface. If the air is damp, you might lose a few because it's a better conductor. Okay? If you get too many electrons, then the force of repulsion might be so big that they keep going a bit. But generally, they're going to stop when they get to the surface. And, by the way, to maximize the spacing apart, and that's what they want to do, right? They're going to be equally spaced. So the charges go to the outside, and when they get there, they are equally or evenly spaced on the outer surface. The next one we did yesterday was a solid flat conducting plate. Now, we're going to focus on charge number 2 here on this solid flat conducting plate. Charge number 2 experiences a force to the left caused by number 3. We call that F32. Experiences a force to the right caused by number 1. We'll call that F12. That's a bigger force because object 1 is closer to object 2. Electron 1 closer to electron 2. So that means if we've got a force to the right that's bigger, it's going to move to the right. But as it moves to the right, F12 becomes smaller. Because as you get further and further away from charge 1, the force of F12 decreases. There's going to be a point when it decreases, and this one increases to the point where they end up being equal. And that's this point right here. The charges, the extra charges, go to the outer surface again, and they are evenly spaced on that outer surface. Now, somebody this morning, I thought, asked me a really good question. She said, like, what's this jaggedy edge down below here? Like, does that influence the distribution of charge? Well, the jaggedy edge is not actually meant to be a jaggedy edge of the material. It's meant to show you that, like, they're only showing us the top part of it, right? We kind of cut it off, and they're only showing the top part. But it does kind of bring up an interesting point. Another interesting question, that is, like, what if that part that's not being shown here is something like this, not uniform? Well, we'd still get an even distribution of charges on the uniform part, right? Down here, all bets would be off because that's not a nice uniform surface, right? The charge distribution down below would look different. So it is possible to get a uniform distribution over part of a surface and then a non-uniform distribution over other parts of the surface. Let's look at our irregularly shaped conducting object, or our pointy metal thing that we talked about a little bit yesterday. We looked at charge 1, charge 2, and charge 3, and we pretended charge 4 wasn't there. The analysis ends up being pretty much the same, even if charge 4 is there. It just becomes a little bit more complicated. The diagram is more cumbersome. Charge 1 repels charge 2 this way, pushes it away. Charge 3 repels charge 2 this way. We'll call that F32. Now, F32 has an X component and a Y component. The Y component of F32 pushes it to the outer surface. Still goes to the outer surface. But the X component, Y component to the outer surface, the X component tries to counter this F12 that's pushing it to the tip. So you got a force pushing it to the outer tip, and then you got a force trying to push it back. But this one wins. So what happens to these electrons? They tend to go towards the outer tip. You get a higher concentration where it's pointy at the outer tip. And a lower concentration back here. They're closer together at the tip. They're further apart where it's more uniform surface. And we used this example yesterday, right? When you're walking across the carpet and you build up that charge by friction as you're walking across the carpet, and then you go to touch somebody, you touch them with your finger, right? And why? Because your finger's pointy. Because that's where the buildup of charge is going to be when you touch them with your finger, right? If you touch them with your hip, or you touch them with your back, your flat back, you're probably not going to shock anybody because you don't have a buildup of charge so much there. They're spread out more. The pointy areas, they're a lot closer together and more concentrated. Yep. That's a good question. Would the spot that you touch them on their body affect things? Absolutely it would. Now, sometimes when you go to shock somebody, you touch them in the back of the neck or something and it works, right? It would work better if you touch them in the finger. Okay? If there's enough potential difference to shock them touching them in the back of the neck, then you would get a bigger potential difference touching them in the finger, because for similar reason, the pointy object on them works better just like it does for the pointy object on you. Yeah, absolutely. We got a belt coming for our Van de Graaff generator here sometime real soon. It should be arriving real soon. When that arrives, we'll do the little demonstration of trying to make your hair stand on end. Okay, why does your hair stand on end when you touch that Van de Graaff generator? Because your hair is pointy. Right, your hair is pointy. And where do the excess electrons go when you're touching that Van de Graaff generator? To the pointy parts, to the hairs on your head, right? So what happens to them? Well, this hair is negative, this hair is negative, and they're going to repel each other and therefore stand up on end. Make sense? All right. Now I got a couple more here for you. This is the one that I think is really neat. The basic analysis of this we've actually already done. A hollow conducting object produces the same distribution as a solid conducting sphere for the exact same reason. So we don't need to go through that again. But there's something else that I want to show you with this one. Okay, notice that the charges have gone to the outer surface and the distribution of the charges are evenly spaced. I want to look at the electric field for this one though. The electric field lines are pointing inward, which makes sense, right? The electric field points towards a negative producer. But look at inside. Look inside. The electric field inside this sphere caused by this one points this way. The electric field caused by this one points this way. And the electric field caused by this one points this way. And of course, if we had 1,000 more electrons, we could draw the electric fields caused by those as well. We're not going to go through a mathematical vector analysis of this, but if we did, if we broke each of these down into X components and Y components, and then combined the X's and combined the Y's, What do you think the net electric field would be? What do you think they'd add up to give me? Zero. They would give me zero. The net electric field inside a conductor is zero. We call this a Faraday cage. A Faraday cage is a conducting surface where the electric field inside is zero. It's not that you don't have electric field inside per se, but it's just that the electric field cancels other electric fields out. Now, we looked at the electric field right there smack in the middle, but we'd find the same thing here. Okay, we'd find the same thing wherever. The electric field anywhere inside that Faraday cage is zero. So it's a little bit counterintuitive, but listen, if you found yourself in a lightning storm and there happened to be this big metal ball on the side of the road, even though that big metal ball would attract lightning, you'd actually be safer inside the thing that attracted lightning than you would just standing out there on the side of the road. Okay? It would attract lightning because it's a conductor, and it would transfer electrons into the ground pretty easily if it was sitting on the ground. But you inside it would be completely 100% safe because the electric field inside is zero.
But you couldn't be touching.
No, even theoretically you could be, because it's not the inner surface right here that has the charges, it's the outer surface that has the charges. Does that make sense? You ever heard that a car is the safest place to be in a lightning storm? It's true. Or at least it's one of the safest places to be in a lightning storm, but it's not because of what everybody thinks. Like, oh, I know what it is. It's the rubber tires on the car. That's why it's safe to be in a car in a lightning storm. Like, the lightning just went from the cloud to your car. It can't make it through the half-inch of rubber? Like, I have a half an inch of rubber on the bottom of my shoes right now. Does that mean I could just stand outside in a lightning storm and hold up an aluminum baseball bat and be safe because I have a half an inch of rubber on the bottom of my shoes? Of course not, right? It's nothing to do with the rubber tires on the car. Nothing to do with the rubber tires on the car. Lightning, the electrons that strikes the car will easily go from the car to the ground. Easily. Why are you safe inside a car? Because the car is a Faraday cage, and the net electric field inside the car is zero. Even though it would be scary to get hit by lightning in a car, you'd know it. It would be scary, but it wouldn't hurt you. It wouldn't affect you in the slightest, not physically at least. Last one. We're going to talk now about a parallel plate capacitor, and what that means. What a capacitor is really is a couple parallel plates, charged parallel plates, that can store charge. Okay, you can store charge for later on so that it can discharge later on. Don't worry about that so much. Okay, I want to focus on, first of all, this bottom plate of these two parallel plate capacitors. It's negatively charged. So we have a bunch of extra electrons in this. Okay, what happens to it? Well, they go to the outer surface. Some people will say, no, that's not the outer surface, that's the inner surface. No, if we pretend that doesn't exist for a second, that's an outer surface, right? The electrons, the extra electrons are going to an outer surface. Now, right here in the top one, it's not that the protons are going to an outer surface. There's protons everywhere. It's just that we have less electrons here than we have in other places. So the electrons have left the outer surface and been in other places because it's a net positive charge. Now, what we want to see from this is not so much why they go there, because we saw that with this other slide back here, but rather what we want to look at here is, just like we did in the last one, not so much where they go and why they go there, but the electric field that's produced as a result. Here we get an electric field between positive and negative. Another one. And I think we showed you yesterday or the day before, there's actually these fields as well. These curved ones end up canceling out, though, so that we end up with this nice uniform electric field between the two plates, going from from the positive plate to the negative plate. You get those edge effects. I think I told you about those. where it kind of curves outwards, non-uniform field, but we don't worry too much about that. We're not going to have to use that in any kind of analysis. All right, so parallel plates, charges still go to the outer surface, but because of that, it creates for us this nice uniform electric field between these two charged parallel plates. All right, here's your homework for tonight. And you've got a few minutes, about 7 minutes to work on it here. Page 569, we've got number 4 to 7 and 9 to 10A. You do not need to do number 8, and you do not need to do number 10B. So 4, 5, 6, 7, and then 9 and 10A.